we're going to talk about sorting. Again, we talked about sorting. We talked about sorting in algorithms a long time. It was like the real beginnings of the whole issue of measuring how long an algorithm took. And we started with sorting, which was like the ABCs of algorithms, and then we moved on to a million more difficult things. Now, why didn't I finish it up and do this lecture back in algorithms? Why did we wait until we got to the database course before we do this lecture now? So there's two reasons. For one thing, maybe the most common application of sorting is in databases. And I want to ask you where you think that happens in just a second. But two, before I do that, the other reason we wait till now is because in algorithms we're concentrating on understanding the theory of analyzing algorithms, the theory of designing them and figuring out how long they take, independent of the machine you run it on, independent of the configuration of the machine. You want to say this is an order n log n. You want to say this is order n squared. And you want to be able to talk about it in a mathematical way that everybody can agree on so that when you get an improvement, you don't have to go ahead and do an experiment on it. Nevertheless, and I hope I really stress this in the algorithms course, that's not always the whole situation. Very often, constant factors matter a lot, especially in actual implementations. So the whole discussion today is talking about how do we do sorting with the particular restrictions that come up technologically in a database system that have nothing at all to do with order n log n or order n squared, but have to do with constant factors. Everything we talk about today is completely a separate, independent idea of what we talked about before. We know how to do sorting, but now if we try to do it, everything slows down by a factor of 1,000. How can we get that slowdown to be just a factor of 2 instead of a factor of 1,000? That's really the idea. And because of that, it's really an engineering lecture. It's an issue of come up with the most clever idea you can to twiddle the particular system we have because of the specifications and restrictions that we have in order to make it run practically fast. So we're not going to be proving things or doing too many formulas. Most of what you do in this kind of situation is do experiments and do tests and actually run it on particular machines, under particular systems, under particular configurations, and see what actually does well and fine-tune it and test it and calibrate. And there's no right and wrong answer. Just understanding what you're going to measure is the most important thing. All right, so that's the big picture. So before we go on, I want to back up then to the first idea, that sorting is one of the most common things that happens in databases, and in fact, databases represent maybe the most common application of sorting, vice versa. So where does it come up in databases? When do you sort? Why do you sort? They talk about it at the beginning of your chapter if you read it, but you might have your own ideas. I mean, what do you think? Let's come up with some ideas. Sorting. When? Searching.
Enable searching.
Okay, what does that mean? Because searching for what?
Well, if you sort your data, you can then do a binary search and pull out a range of data.
Okay, sure. If you sort your data, it's easier to find stuff.
Sure.
But do we actually do that in a big database? Do we sort the data and then search for stuff? We usually store the data like a big B+ tree, right? And then we search for it. So actually, so for searching, you don't have to sort things, although you could. So Chris is right. If you could sort things, you can certainly search for things, but it's not necessary. You can store things in some kind of nice tree format, like a B tree, or if it's internal in the computer, a red-black tree, and get fast searching times, even without sorting it. In fact, you can even use that search structure to do sorting if you want to. You can use a B+ tree to do sorting by just looking for the values looking for in order of the key that you sorted the B tree on. So you can kind of do it vice versa. But certainly that it's true. I mean, you can certainly use sorting for searching. So I'll put that down. What else? There's lots of reasons. What else?
Lots of things are done in alphabetical order.
Right, I mean, you have queries that say blah, 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 select this, from this, where this, group by this, sort by this, right? I mean, you sort all the time with queries. Humans like things ordered. So some queries have sort by in them. What else? What's my little list? I still got some more.
Well, joining is a case of doing a series of searches in order to figure out what.
Right. I mean, you probably haven't talked about this yet because the idea is you'll talk about this tomorrow and the day after. How does a database actually do these joins when you tell it to do a join? Right, the whole idea of a database is to keep a level of abstraction between you and having to figure out how to do that stuff. It's stored at the hardware level. You study that. You study how you talk to the database through the query language. But how do you go ahead and actually do the things that you ask the database to do? I mean, that's the guts of the database. That's these companies that build databases. Oracle presumably knows how to do that well. They spend a lot of time making sure that when you give them a query, maybe where it asks to join something or it converts your query into something where it needs to do a join, that it can do that join quickly. How do you do a join? Magic, right. Right. At the level that you guys use it, it's magic. So how would you do it if you had to do it and you just have these, you have a huge table, say, I don't know, say you want, you got employees, you got the departments, you want the manager ID to equal this ID. How do you do something like that? Okay, you can just do a nest.
Presumably whatever is the joining variable, if it were sorted, it would be a quicker operation.
Exactly, right. You could do this nested loop, and it would be a lot faster to do this nested loop if the actual variable that you were trying to join on were a variable that the second table was sorted by. Then you could go ahead and find it faster. So doing joins is fundamentally faster if you can sort by a particular key. So the implementation, or what's sometimes called query optimization, it's an important topic. How you go ahead and actually implement these things. Sorting is like the ABCs. It's an important step. We got to be able to sort these very, 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 very huge tables that might have 500 million entries in them. All right, what else? That's a very good one. Very practical. I'll put a star there. Maybe it's the most important. There's one more simple one that comes up. What if you just remember what project does on a relational algebra? What does project do? Right, it pulls out a column from a table, basically, right? Now, if you don't project over a primary key, what can happen in that column?
Duplicates.
You get duplicates. And what does Oracle or whatever database you have usually do? It usually collapses them and doesn't give you duplicates, because why the heck would you want to see the thing show up more than once? And if you did, there's a way to make it happen, or you could count it. But normally you don't want it to show up more than once. So how does it get rid of those duplicates? Right, well, one way, I could have given you this in algorithms, okay? In fact, I probably did. Here's an array of values. There might be duplicates in them. Get rid of all the duplicates. I want just the unique ones. Well, one fast way to do it is to sort the whole list first, and then go through it. And if you ever see something occurring again, delete, 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 until you get a new one. And then, go on that way. So you can do a linear scan getting rid of duplicates once it's sorted. And the sorting takes n log n. So in n log n time, you can get rid of duplicates. If you try to do it in some other way, you'd probably end up getting it n squared. Like taking the first one and looking through the whole list to see how many times it occurs, and then taking the next one and looking through the whole list, that's n squared. That's too slow. So just using sorting as a preliminary step ends up getting rid of duplicates in n log n time, which is, I don't think you can do better. I don't think you can do it in linear time. At least it doesn't seem likely. Whether you can or not is a topic for a different discussion. But getting rid of duplicates in project queries. And there's a lot of other reasons. You need to sort data. Databases is all about data. All right, so I've convinced you need to sort stuff. Now we have to figure out, why is this lecture different from the one we did in algorithms? And I want to start off by trying to convince you it's not different, and let you convince me that it's different. So I have somebody.
Halfway down.
Somebody puts them on my desk. I get a lot of people to help. We want to sort a billion items. Let's put it another 100 billion. Let's go wild. 100 billion items. We're really sorting a lot of things. Now, your typical main memory nowadays, even in a good machine, is like, what is it, 256 meg or something?
Well, on a server, it's in the gig range.
Okay. I made this big enough that it's not going to fit. All right, so here's what we can't do. We can't go ahead and just stick it in RAM. It won't fit. It won't fit with the operating system. It won't fit with our sorting program. It's not going to fit. So what do? Well, I won't put it in RAM. I'll just leave it on the disk. Right here, it sits on the disk, all these 100 billion things. And I just put my program in RAM, the one that's going to do sorting. What's the fastest sorting algorithm we did? Quicksort. It's pretty darn fast. We should point out, though, before I go through, we're going to try to do quicksort here for a second. But before I do, remember that we measured sorting by a lot of different metrics. There was time. Quicksort is n log n. That was one metric. It was an important metric, the time. Right? There were other metrics. What were they?
Space.
Right. So space had to do with whether we could do it in place. Whether we needed extra copy of the space that we got our data in to begin with. And some algorithms could be done in place and some couldn't. And sometimes that's very important. It's pretty darn important here. We certainly don't want to copy these 100 billion over any place. What else? What else was special about sorting that we distinguish between algorithms, regardless of how...
Whether they're stable.
Stable, right. What did that mean? Oh, yeah. Stable. Stable means that if you have two things, two keys that are the same, that they stay in the same order after you're done sorting that. And that's very important if you're sorting records, where if you have two things, say, with the same student ID, and they were already sorted on some other feature before, you want them to stay in the same order that they were. So that's something important. You don't want to use something that isn't stable if you absolutely need a stable sort. All right, what else was important? What else was another feature? Yeah, you have a question, Jeff? You're just thinking?
Yeah, on that stability, why wouldn't they stay in place?
There's lots of sorts.
I missed that.
Yeah, there's lots of sorts where things that are equal get moved out of place.
Meaning in the process, even
Yes.
though they end up the same, even though they end up next to each other.
They'll end up next to each other, but not in the same order they were when they started.
Oh, okay.
So if there were two 6s in the file, one up here and one over here, they might switch places by the time they're done, even though they'll be in the right order with respect to the other numbers. And that could be bad if we've already sorted this file on some other key and wanted to keep that consistent.
Yeah.
It's a good question. It's not obvious why it would switch. There's other metrics. Here's another one that we mentioned. What if the thing's mostly sorted? You know it's not too far off. There are some algorithms that really finish it off fast, and some that do just as bad as they would if the thing wasn't sorted at all. So there's all sorts of special things about data that make you want to pick one sort over the other. It isn't always obvious what to do. What else? There's one more that I can think of. What if the data values are restricted? What sorts work well if you say all the data is between 0 and 100? Radix sort and bucket sort and counting sort. If you know that the data itself is restricted, you can almost do the sort in linear time. So all these things matter. So when you all answered me a second ago, let's do quicksort, that's true. If I don't tell you anything about the data, let's do quicksort. But if you know anything about the data and you're familiar with it and you really know something specific about your particular application, it might not at all be the right one.
Especially if it's mostly sorted. Quicksort's bad.
If it's mostly sorted, quicksort's very bad, right? It has no idea. You could probably fiddle with it to make it better, but... All right, well, let's go ahead and do quicksort on this. Let's pretend we remember what quicksort is. I remember. We have a big array that's 100 billion. Well, we don't really have a big array, do we? We have a big file with 100 billion key values in it on disk. And quicksort takes the first element of that big file and partitions the array around it, so that when it's done, it has that first element somewhere in the middle, and all the things smaller than it to the left of it, and all the things bigger than it to the right, and we don't care what order they're in, but it partitions it. And then it recursively does the sort on the left part and the right part. Remember that? Does that ring a bell? Okay. And it turns out that the average case is n log n, that you tend to get things more in the middle overall than you would splitting it 1 and n. So you tend to, or 1 and n minus 1, you tend to, the n over 2's win out. Now that's fine, but what actually happens here when we try to do this partition? If you remember how you do the partition, you take this one and you put two little pointers, one here and one here. Right? And you compare these to that key value, and if they're not in the right place, you switch them, then you move them forward. What actually happens every time you want to get another value to look at it? What happens in a system when you want to go ahead and look at a value on the disk?
Disk I/O.
Right, you have to, right, actually, first you check if it's in the cache, if it's not in the, first you check to see if it's in RAM, right? If it's not in RAM, you say, okay, I don't have this, so I have to go to the disk, and here's what the disk looks like. I should have brought the one in from the other room. And it's like, move to this track, rotate the disk, pull the data off. Dum, ba-dum, ba-dum, dum, 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 dum. I mean, this blazingly fast processor that's doing 1 billion operations a second is waiting for this pathetically slow mechanical device to move itself to the right track, rotate itself under the right spot, and then transfer all the information to the very, very fast semiconductor memory. And then you can actually do this comparison. Now the next comparison, what's going to happen? Are you going to have to go to the disk and do another one of these things? Well, when you do disk I/O, you get typically like 1K or 4K. You get a few thousand in. So hopefully we'll be lucky. We'll have what's called spatial locality. And we'll be lucky, and the next actual access goes right to RAM. Okay, so that's one fast access. And then the next one, maybe we'll get lucky again, and sooner or later, we're going to have to go to the disk again. Now, yeah.
Just deal with all the stuff in RAM, like just take it, deal with that. I mean, that's efficient, right?
The stuff when it's in RAM is efficient, sure.
But you don't have to go to the disk again until you...
We don't have to go to the disk again until we actually get a data value which is not in RAM right now. So what's the issue here? The issue here, let's get some real numbers. And accessing a value that's in RAM is on the order of nanoseconds, and accessing a value that's in the disk is on the order of milliseconds. So 1,000 times, 1,000,000 times faster to get the value in RAM over the value in disk. So you do not want to have to go to disk. I mean, it's gruesome. It's a constant factor, but it's a horrible constant factor. If we just went to the disk every time and did our algorithm, it would still be n log n. That would be the RAM version. And the disk version would be 100, well, no, 1,000,000 we said? 1,000,000 n log n. Right? So they're the same as far as algorithms people are concerned, but you can't sell a database that does this, and you can sell one that does that. So the whole idea here is we want to knock this 1,000,000 down. Okay, we don't want to do every single time we hit a value, go to the disk. Now it's true, in this example I came up with, we're not going to the disk in every single one, but we're going pretty often. We're going to go probably every 1,000, right, or so. So that means this will get cut down to 1,000 n log n. That's a little better, but we'd like to knock this down to something like, 2 or 3 or something. Wanted to make it nice and easy. Or the best we can do. We want to just knock that down. Now, what's the way you'd really do this? You'd really do this just the way I described, basically with virtual memory. You pretend that you have access to the whole hard drive, and every time that you don't have access, then you pull a page in. That's what virtual memory is. You let your operating system do it. And you could actually sort like this. You could say, put my 100 billion things in virtual memory, make the whole disk available to me, and now I'm just going to do an algorithm, and anytime I don't get something in RAM, I'll run over there and I'll pay a price. I'll pay a price that's 1,000,000 times slower than I normally do, and hope that the operating system virtual memory system will make sure that you get hits most of the time and misses very infrequently. The thing is, with a file this large, you can't really guarantee that the operating system is going to be able to help you too much because you've made your virtual memory space just way too big. But you do what you can. It's not completely out of the ballpark. There's actually a problem in your text that has you quantitatively check something like this out. Gives you all the numbers and says, see how long it would take. And you do some crunching with your calculator and you calculate it. All right, questions so far?
Got to write it out too. That's a big problem.
Yes, certainly. I mean, anytime you do the swap, you have to change two values. So, but this, if you remember how virtual systems work, you just kind of remember that the page is dirty, and then sooner or later, if that page gets swapped out, then you write the whole page. So you don't actually go to the disk and write every single time you make a swap. You kind of do it in one big write back stage later on. Still, you're right. You do have to write it back, and it takes a long time. Okay, questions? Yeah.
You have two arrows, 2 pointers. As the bottom one works up, you're likely to have those pages already in cache because the disk was read sequentially.
Right.
Could you plan ahead that the rightmost arrow is going to go down? You tell the disk, I'd like 100 pages starting at the end, please. And I'd like 100 page from the end, and it would have read the 100 pages.
Yeah, I mean, when you access this one, it's going to have the page that this one's in. It's also going to have the page that this one's in.
Right.
Yeah.
But as you move in,
as you move in, you're going to
already be there, but it's unlikely the right-hand one will be there because the sequences won't work backwards. You know that your pointers are moving inward, but the operating system on the disk has no idea that you're going to eventually be marching backwards.
Oh, I see. So you want to specifically tell it just to pull in this way. You could probably fine-tune this, and I don't know how. My guess is that I don't think people really do this. So probably when you fine-tune it all you can, it's not as good as the method I'm going to show you next, which has become the standard method more or less. But you're right. Sure, you're right, because this would go forward and this would.
I could fiddle while Rome is burning.
Yeah, you could. That's right. Yes.
One, if we filled up our RAM entirely and dealt with all of that and then filled it up again, that's the best we can hope for.
Yeah, Doug's asking a really good question. What's the best you can hope for? I mean, we went through some scenarios here. What's the best thing that could possibly happen if you cannot get all your data into RAM but you still have to sort it? What's the fastest you can do it? Let's assume, I have to give you some information here. Let's assume that a page, that the amount you can read in at one time from the disk is say 1K, say 1,000. So the best you can hope for, I mean, you've got to at some point access every value here. So the best you could hope for is that you look at every page exactly once on the way in and once on the way out. And when it's in there, you look at all the data you need to, and you never have to get it again.
Like if it were already sorted, for instance.
Yeah, if it were already sorted, for instance, that you get lucky. Right. Well, that's fine, but that still requires us to read in whatever it is, 1,000 off here, 100 million pages and print them back out. That would be the best we could hope for, is to read everything in once and read it out once.
And so the best we can hope for in terms of time?
The best we can hope for in terms of time is n, where n is the number of pages containing your data. N disk access, where n is, in other words, you look at everything just once. So actually, let me push a little further along here, because let's not think about sorting for a minute. Let's think about, I want to take every number in your database and bump it up 10%. This is a much easier problem than sorting. How do you do that? You just take the data one page at a time, you pull it in, you bump everything up 10%, you write it out. You get the next page, you read it in, you bump everything up 10%, you write it out. Okay, you just page by page read the data in, bump it up 10%, write it out. You get a linear number of accesses in the number of pages that you have. If you have 100 million pages, then you just read every page once, write it out once.
It's more complicated than that, though, because you would want to read in big blocks of lots of pages.
Well, depending on how your hardware works. Your hardware, typically, you don't have just room for one page in your RAM. You might have room for, say, 500 pages in your RAM. And Chris is right. there's an issue with hardware. I mean, I was making fun of how slow the disk is. There's 3 parts to the disk transfer. You all know that, right? There's the part where the big arm moves to the left and right like an old phonograph needle. There's the part where the disk rotates underneath to the right spot. And then there's the part where the transfer actually occurs. Okay, so the slow part there is the mechanical part, is the part with the arm moving and the part of the rotation. And then the faster part is the transferring part, which depends on how much you're transferring, but which is relatively small compared to the seeking and the rotating part. So Chris is saying, well, why don't we just, if we're bumping everything up 10%, instead of doing 1 page at a time, why don't we just do 500 pages at a time, bump all those up 10%, and write those 500 back, because then we save the seeking time and the rotating time for each of the 500 separate pages, have only 1 seek and 1 rotate for the whole 500 pages, and just have the transfer time be the main thing. And that's absolutely a good idea. But you just have to have a more realistic model of how the machine works, and that's true. You can do that. Does everyone understand that? That's an important modification that you would normally do. Okay? Questions so far? All right. So there are some things you can do just kind of with a linear pass-through, like bumping things up by 10%. What we want to do is kind of turn sorting into something like that. In my mind, I have this metaphor that works for me, and it's just going to be like the bologna tree. It probably won't work for you, but I think of it like a machine gun, where the data is sitting here outside the processor in these long, ribbons of bullets, and the CPU just reams them through, processing them, the shells flying out, and out comes the sorted data on the other end. And the idea is that if you can really do it that way, then you look at every page exactly once, where every bullet is like a page. It just comes in, goes out, you never look at it again. In the quicksort version, you might have to look at a page many, many times. I looked at it now, I had to write it back to memory because it changed, and I had to swap a page out, now I have to bring it back in again. That's the worst thing. That would be like running your machine gun through, and somewhere in the middle, stopping the machine gun, rolling the thing back, and running it through again, just to get through. You're not going to defend the castle that way. It's too slow. All right, so can we think of a method for sorting that has its main tool something that works in linear time? And I told you this when we did algorithms, so you should probably know the answer. But the one we're going to use instead of quicksort is, who remembers? Which sorting algorithm has a linear time subroutine that's most of what it does? Merge sort, right. It's not so much that it's linear time, it's more that, well, it's more that you can scan it from left to right and never look at it again. Let's think about this. Now we need to see an example. You all remember merge sort, I know, but just in case. All right, here's just a quick review of merge sort, and let me tell you where we're going. You need to remember how merge sort works, because merge sort is the basis for what in this book is called external sorting. External sorting is the idea of sorting things when you cannot get them into RAM at the same time, and you have this horrible issue of the constant factor multiplying by 1,000,000, and you want to knock down the number of page accesses, ideally to the linear number of pages in your whole data set. So we're going to do this by imitating merge sort. So here's a review of how merge sort works. When we start, we'll just imagine that we have just this many numbers. A power of 2 makes it easy to analyze. And each number on its own is a sorted list. That's kind of the base case. You don't do anything with single numbers. They're already sorted. And now you do what's called what the book likes to call a pass. You pass through this data, and you merge pairs of sorted sublists. The book calls sorted sublists a run, R-U-N. Okay, so here's 2 terms you should use, because I'm going to use them from now on. A run is any sorted sublist of your data, and a pass is a collection of merges that goes through the whole set of data and merges pairs of runs into other runs which are twice as long. Okay? You should know that terminology. The book uses that. So what happens? These two go together, and they become a sorted pair. These two go together, become a sorted pair. These two go together, become a sorted pair. These two go together, become a sorted pair. That's pass number 1. So now we have 4 runs, each of which has 2 elements in it. And now we go through the data one more time. This becomes 8, 15, 16, 18. This becomes 3, 5, 10, 19. So after our second pass, we have 2 runs, each of which has twice as many things in it again. So 4 things. And finally, the last run has the sorted list in it. 3, 5, 8, 10, 15, 16, 18, 19. And that's how merge sort works. Okay, questions about that idea? If you remember how we analyze merge sort, every one of these passes takes how much time? Merging 2 things takes time proportional to the sum of those 2 lists. It takes 2 steps to merge 2 things. It takes 4 steps to merge 2 pairs of things. It takes 8 steps to merge 2 things of 4. You keep a pointer to the top of each one. You compare which one's smaller, and the smaller one moves into the other set. You move that pointer down. Every step you move a pointer down. Sooner or later you move both pointers down through each list. Merging is an operation that takes time proportional to the sum of the 2 lists. So merging all of these takes how many steps? All the merges put together. 8 steps. All these merges put together takes another 8. This last merge takes another 8. So every single time you do a pass, it takes time proportional to the number of data values you have, which is n. And how many passes do we do? Log base 2 n. Enough times to have the 8 to get down to 1. So here's the complexity of merge sort. N log base 2 of n. Or just n log n, because we don't really care about the base in algorithms. We will care about the base a lot in this chapter. It's like the whole point. All right, this is not doing it on a disk. This is not doing it externally. This is just a review of merge sort. You can also think of merge sort recursive, which says recursively merge sort each half, the first half and the second half, and then merge the 2 results together. And if you think of it that way, then you come down here in the recursion, and this becomes the base case, and then you push your way back up this way in the merging. So you can think of it iteratively or recursively. Any way you're comfortable with, it works the same way. All right, questions about this? We're not going to do a recurrence equation for merge sort. We're just going to analyze it this iterative way. All right, so log n passes, n for each run. I'm going to mark that down. This is the number of passes. This is cost of each pass. Okay.
Do you need a +1 or a
No, the book's just wrong. Now, I don't think you do. Let's take a look. Here, we have 8 things, right?
Yeah.
So it takes 1 pass, 2 pass, 3 passes. Right? There's only 3 passes. You don't do anything at this stage. And here's the machine gun metaphor. Every one of these, where you have 2 things coming in and 1 thing coming out, the machine gun sits here. The machine gun takes, here's the CPU, that's the real machine gun. It takes 2 sorted things. Sorted A, sorted B, and outputs the combination of sorted A union B. It merges them. And the thing about merging is you don't have to have everything in at the same time to do merging. You can bring things in pieces at a time. How do you do merging? You just keep that pointer here at the top. This is the most fundamental idea. So I'm going to slow down and say it again. This is why we use merge sort. It's because if you have 2 billion things that you want to merge together, you can bring them in 1,000 at a time and merge those guys together, writing them to another place in your RAM, and when that place is filled out, spit it out to the disk. And when your input runs out, just bring in the next 2 pages, fill them in again. Your machine gun keeps bringing in more and more pages of data, and you keep merging as you need. So you always have these 2 input buffers, 2 places where the input comes in. If one of them runs out, because it's much smaller than the other one, then you just fill that one up before the other one gets filled up. Anytime an input buffer empties out, you read another page from the disk into the input buffer. So they act as the little reservoir inside the CPU. The CPU does its job, spits out an output page. Whenever that gets filled up, out it goes to the disk. So that's the key thing about merging. You don't have to see all the data at once. You can bring it in a piece at a time. Everybody gets that? All right, I said it so many times because it is the main idea. The rest of this is all engineering and calculations.
Is the book really wrong, or are they just counting different numbers?
No, they're really there. Oh. I will explain exactly why the book has the +1, so I don't have to fudge it. And then you'll see why I think it's a little subtle. I won't say they're wrong. I'd say they're mildly misguided. I really don't like the +1 there. I think it's easier to describe without it, and everything's simpler. And I'll tell you why they have the +1 in a second. In fact, 1 second. Right now, we're up to there. The next thing I will say is, are there questions before I say? All right. All right. Cost each pass. All right. These are just numbers. If you were doing this in an external sort, then each of these numbers represents a page that you start with. So each one of these circles, let's say a page, what's a typical size for a page? Like 1K, 4K, in the thousands. So let's say every page is 4K. 4K values. Right, we're going to talk about that in just 2 seconds. So, not even, we're talking about it right now. All right, so instead of one number, we're talking about a page of numbers that's 4K tuples long, or records long. And we want to go ahead and do our first step. Now, what was the base case in this merge sort where you have one single number? The base case is do nothing. A 1-element list is sorted. The base case here is not that simple. You have a page with 4K elements in it. It's true that you don't want to merge it with anything, but it's filled with numbers. You've got to sort that page. So you bring it into memory, into the CPU. You let it chug on this. And what sort do you use? Well, it doesn't make a darn difference because it's in RAM. So use a really fast one. Quicksort is probably the best one to use there. Different database systems use different ones. Some use radix sort, some use insertion sort. Depends on how big the size pages they're bringing in. But everybody uses a different sort for this base case. It is not at all the merge sort that the whole thing is based on. This is the base case, and it can be any sort you want. So sort each of these pages. Now what do you do once you sort each of these pages? You read a page in, you sort it, what do you do with it? Right, the book spits it back out. So read in the 8 pages one at a time and spit them back out. And what do you do? That's pass number 1. I don't do anything in pass 0. The book reads all these in and sorts them in pass 0 and then spits them back out. So it reads all the pages in, reads them out. And you're thinking, well, you have to do that. Well, sure you have to do that. But now what does the book say to do? Read them all back in again and merge them. Well, we had them in just 3 seconds ago. Right? Why did you write them back out if all you're going to do right now is read them back in and merge them? Read in the 8 pages, sort each one, and then merge them. There's no reason to do a read and a write in this first pass. The book's got the +1 because it counts past 0 as 1. It counts past 0 as 1, and to give them some credit, because it's not fair to badmouth things out of context, they do this for what I think are mildly decent pedagogical reasons, because their generalizations of the next sections work on this, and they make an improvement on the past 0 in the next sections. So they're going to show that you don't really have to do it this way, but I still don't like it.
It's processed differently past 0, because you have to do the quicksort. In the other passes, you just merge stuff.
That's true. That's true. But the key thing is you do not have to write it back and then read them in again before you do step 2. So anyway, so as far as doing your problems go, because you're going to actually have to calculate numbers here, you can do it the way the book does it, but if you understand what's going on, don't do it the way the book does. I mean, you can just be consistent the way you're counting it. Explain what you're doing and explain why there's so many passes. And if you want to do it the way the book does it, say I'm doing it that way and I'm going to read it all in and spit them back out regardless. Because there is some justification for thinking of it the way they do it. All right, so let's get back to the big picture. So that's where the +1 comes from. So I don't think it's wrong. I just think it's a little misguided. So the book goes ahead and has pass 0, pass 1, pass 2, pass 3. We just have 3 passes. The first pass is read all the information in, sort each page, merge them into pages which are twice as long. All right. Now, when you merge them into pages that are twice as long, this is 8K. How many I/O accesses are necessary to do this one little section? 1 to read this page in, 1 to read this page in, and 2 to write this one out. Okay? So it's 1 read and 1 write for each of these. And that's what happens for all the other ones as well. In every single phase, we read a page in, we write the page out. We read the pages all in again, we write the pages all out again, we read the pages all in again, we write the pages all out again. So how many page accesses do we do all together? It's twice, because it's in and out for every page. The number of pages in a pass, which is, we'll call it n. Now n is the number of pages, not the number of values in the database, but the number of pages of values in the database. 2 times n, number of pages, times the number of passes, which is log 2 n. No +1. There it is. And if you have an extra pass, then you'd add a +1.
And we're just ignoring the actual sorting and merging because it's much
Right,
so
right. Each one of these steps is 1,000,000 times slower than the actual steps inside of doing the merging. So we're presuming that this is the main cost. That is completely not fair. I mean, there's a lot of work that goes on in the CPU, and it does add up. And in fact, the whole idea, when we finish this lecture, we're going to talk about a technique of double buffering. And the idea of double buffering is specifically assuming that the time it takes to do the processing inside is at least as long as the time it's going to take to read the next page in. In which case, you should assume more or less that whatever you get here, time-wise, it's going to be just about the same, in other words, double altogether, as the time it takes to do the internal processing. That's the perfect balance. This is all engineering. This is not algorithm analysis. This is engineering. We want to balance our resources. We have an unbalanced machine that can do some things very quickly and other things very slowly. We want to balance it perfectly, so we use as little of the slow stuff as possible, but keep the fast stuff working exactly as much time as the slow stuff is doing its job. And that's what we're dealing with. So the rest of the lecture is all about how to fiddle with this a little more, how to make it a little more efficient, how to think of other trade-offs, and then do experiments and see which one works. Okay. Questions so far? Ty, you thinking?
Ceiling of log 2n? Or do you kind of...
Yeah.
Letting you use the fine sequence notation.
My answer to that is, all my examples are powers of 2. And if I were writing if I was writing a textbook, I'd figure out whether to use ceiling or floor, which the book, I must say, is very careful about. They use ceiling when it should be ceiling and floor when it should be floor, and they're correct. And got it.
So, Shai, what is the space usage then for this method?
So space usage, you mean inside RAM?
Well, I mean,
Because that's what we normally measure space
you're
with.
eventually, in your little, right, but in your little machine gun,
analogy, right? You're eventually sort of reading in these sort of larger and larger bullets.
Right.
And doing the
Right.
merging and sort of writing that back out. But the whole example we started off with 100 billion records was an example in which we didn't have enough RAM to sort of get the whole enchilada. So it seems like if we have 100 billion records and, you know, the tree that you have on the left side of the board there, you know, extends way out.
Right.
Eventually, as we move towards this point, we're going to be getting bullets that are too big to read into a range.
Yes, at once. But the key thing is that we can, for example, let's say this represents 4 billion and 4 billion.
Okay.
So what you really do here is you read this in teeny little pieces, a page at a time.
Okay.
And this in a page at a time. And you merge those 2 pages, filling this up. When one of those pages runs out, you read the next page in and you keep merging.
So
you never actually throw all of these in the RAM at the same time. It's a really good question you're asking, and it's an important thing to distinguish.
okay, so then I mean we have these two little bullets, and so as we're moving through, the amount of stuff that we have to write out is sort of twice the space that we've read out of any one of these bullets.
Right.
As we go. So does this mean that we need a whole another storage space for 100 billion records on our disk as we write?
No. We can just write it back to the places that we're reading off of. I don't think we need
Maybe
double.
one extra page.
Yeah, we need one extra page on the disk maybe. I think we can reuse the space without any
So-
trouble.
Okay, so we're not writing back sequentially.
No, because the idea you can do in-place merges. You can do in-place merge sort, which means you can reuse that disk space to print out the pages of the output of the merges without having to worry. But if you did it just naively, maybe you would need an extra, 100 billion spaces on the disk. But I haven't talked about that at all. I'm kind of just letting that go for now. But Kevin's question is really important. It's important to realize that we're not bringing in bigger and bigger and bigger chunks into the CPU. We still bring things in one page at a time. It's just that even if you have very, very 2 long merges, they can be brought in a page at a time and go right through that machine gun without losing any information. You don't have to see the whole merge at the same time in order to merge it. Right. So the analogy with it, there are machine guns that spit out, 100 bullets at a pop or something, right? Horrible, or 30 bullets at a pop. Who knows about guns? He knows about guns, yeah. I think there are guns that routinely spit out, a bunch of bullets at once. So think of the amount of bullets that the gun shoots out as the size of the page. I don't know anything about guns. I went to this Penn and Teller show a few months ago. I told you about it. And they had this gun trick, which is really cool. So they asked for volunteers from the audience who know about guns, and they get these 2 guys who come up. Where do you know about guns, sir? Oh, well, I'm an ex-cop. I go, oh, okay. And he shows him the gun, and he checks it all. And he goes, where do you know about guns, sir? Oh, well, I work for the mob and I assassinate people. I don't know. It's like, all right, don't give that guy the gun. Yeah.
If you're sorting like a field of a record, you wouldn't be bringing the whole record in with it. You'd be just bringing the value in that you're sorting. You'd be sorting the index.
Right, you're sorting on the index of the record, right.
So you'll need another billion to store that. Sorted, it's already stored in the record.
I guess you could be spitting out. Yeah, I'm going to hedge with a yes maybe. Yeah, probably. Here, it's a big it depends, and I haven't thought about this aspect of it because usually we have plenty of space to double what we've got on disk. So I don't think it's so much of a concern, but it's certainly something to think about, and I don't have a good answer for it right on the spot because I haven't thought about it before. It's a good question. Other questions? All right, so we're gonna raise the volume a little bit and do this a little more efficiently. And by that, I mean let's think about the way the machine really works. And there's one thing here that's just not realistic. Okay. Well, remember the best case we're going to hope for is that we look at every page once. that we get n. That was Doug's question, right? We get just one page in and out, or 2n, right? 2n, one in and out. And now we've got 2n log base 2 of n. So basically what we're going to try to do is get this log base 2 of n smaller. And that's the best we can hope for. And let's think of how we can do this. Well, it's not a really complicated idea. It's just a lot of plugging away. Where did the 2 come from here?
We're merging 2 lists.
Because we're merging 2 lists every time together. Right? What if I merged 3 lists every time together? It would be log base 3 of n. If I merged 35 lists every time together, it would be log base 35 of n. And which is smaller, log base 2 of n or log base 35 of n? Log base 35 of n is smaller, right? Right, so what we should do is instead of putting 2 things in here, I mean, after all, it's completely unrealistic just to use 2 input pages, input buffer pages. How many pages do you really have in RAM? You got a lot. You got a few hundred, maybe 1,000 pages of free space to use. Right? Every page, even if it's 4K, 1,000 pages is only 4 meg. You got plenty of room to throw data in that RAM. So instead of 2 pages coming in, we're going to send in, say, 500 pages in a merge. But not in my example. In my example, we're going to do 6, because I can't write 500. All right, so let's say, here are the buffers. 1, 2, 3, 4, 5, 6. Here's the CPU, or the CPU and RAM. So now let's say we have 7 pages. Like I said, it would normally be like 500 or 600. You'd have 1 for the output spot, where you actually put the merged answer. And when this gets filled up, it gets sent out to disk. But when you send things in, instead of sending 2 things in and filling each one up when they run out, you send 6 things in. And when each one runs out, you fill them up. Now, this is a perfectly reasonable generalization. And what it does is it just changes this 2 to a 6. Now, in the book, they call this B minus 1, because B is the number of free pages in the buffer, and one of them is used for the write. So they subtract 1 from it. So when you see that, don't get confused. In my case, this would be 6, because it's 7 minus 1. That's it. Well, it is more or less it. I mean, that's the whole trick. So now, whenever you do anything that's engineering, that's meant to give you a constant factor improvement, there's almost always a trade-off. You just don't get something for free unless your first idea was really lame. This first idea is not lame. It's kind of a decent idea. So where's the trade-off here? What did we lose in knocking log base 2 down to log base 6? I mean, we got an improvement, but what did we lose?
Well, the CPU has to work harder to sort all that.
Right. The CPU has to work harder to sort in every stage. It's much easier to sort 2 merged lists than it is to sort 6. How much easier? Well, let's think. Say I have 10 numbers in each list, and I want to merge them into one big list of 30. How would you do this? You know how to merge 2, right? Remember, we keep the pointer at the top of each one. We do a comparison. Whichever one's smaller, we throw into the output, and then we shift that pointer down 1, and then repeat until till one list is empty. When that list is empty, refill it. Keep going. What do you do with 3? Is it something very different?
Min operation. You'd have to find the min.
Same, right, good. You keep pointers to the top of each one, but this time, instead of just doing a comparison, you have to find which one is the smallest. So it's a min operation among 3 different things. Well,
It's a sort operation.
well, not even a sort, just the smallest one. It's less than a sort. And in fact, in algorithms world, we would say that the number of buffers that fit in memory is a constant, that it doesn't depend on the data. So we wouldn't even call this linear. We would just say it's constant. It's 3 steps instead of 2 steps. It's 6 steps instead of 2 steps. It's 500 steps instead of 2 steps. Everybody got that? So instead of this taking, 2 times the length of the 2 inputs. It takes 3 times the length of all 3 inputs. It's still linear, it's just a factor of 3. If you had 500 pages, it would be 500 times linear. It's, again, just factors, linear factors. So Jeff is right. You save going from log 2 to log 6, but you pay that every single time inside RAM, which we haven't even added up at all in any of these discussions, that goes up by a factor of 500 if we did it with 500 in every single run. So it's a trade-off. If you made this 500, you're pretty much getting even the hugest files through in just 1 or 2 or 3 passes. Because 500 cubed is a big number. A lot of pages in 500 cubed. All right, so quantitatively, you have to do a calculation. You have to know how fast it takes to do RAM accesses. You have to figure out this extra factor of 500 cost in every single small block that you do in RAM. You have to trade it off with what you saved here in the number of passes. You have to realize that these disk accesses take 1,000,000 times as much time as the RAM accesses. You add it all up, you see which way is better. Generally speaking, this is better. You're not going to get killed so much in the RAM as you are in saving passes. It's really worthwhile to save 3 or 4 million than to just add a factor of 500.
Well, I'm a little confused when you've read all the buffers, read all the pages in your 500, say. So aren't you just doing a sort on the 500 pages worth of data?
So
The initial sort on the pages.
yeah,
I mean, that's where the CPU time seems to come.
yeah. Let's contrast the way these two things would work. In this example, we read in this one and this one, merge it to this one. Then we read in this one and this one, merge it to this one. In this example, we read in 500 things, sort each one, merge them all together, write it out in stages.
In the process of merging them all together, you output a sorted.
And you output that sorted thing page by page.
Right.
So you still go ahead and read in and write out one page for every single time you process that data, and you only process it as many passes as we have, which goes down because of the huge branching factor.
Right.
Yeah. Does that answer your question? Other questions?
You just fill up that one buffer, the output buffer. You just fill it up and then write it and then fill it up.
Exactly. Fill it up and write it, fill it up and write it as you go. That's the reason we use merge. Because you can't do that with other sorts. You can't do it with heap sort or quick sort. The thing about a merge is you chew a little bit off, spit it out, chew a little bit more, spit it out. Here, there's a more pleasant analogy. Better than the guns. All right. So in the book, you should realize that with the 6, they still have the +1. And there's a little bit of a, here you'll see exactly what they do. I'm going to give you the version. My version here would have 2n log 6n. And the book's version will be 2n log 6 n divided by 7 plus 1. That's the book's version. Why is that? Why does the book have that compared to me? First of all, compare these two. They are very close. Log 6 of n divided by 7 is log 6 of n minus log 6 of 7. Log 6 of 7 is about 1. Right? Minus 1 plus 1, they even out. So is the book wrong here? No. Now they're very close to right. In fact, their formula is actually a teeny bit less than my formula, just the teeniest fraction less, because there's a little bit more of a minus. Log 6, 7 is a little bigger than 1. Right? So now they're right on the button. But this is a lot more complicated to figure out where this crazy formula comes from. That's not so crazy, and compared to this. So let's think about it for a second, because you're going to read the book and you're going to need to understand it. Where does that come from?
First pass.
Right, it has to do with the first pass. So what the book does in the first pass, let's say this is 7 buffer pages. In the first pass, they don't read in 6 things and merge them together and spit them out like I say to do. You know, they do what they did before. They read in all 7 things and spit them back out. Okay? That's pass number 1. That's why they have this extra +1, because they have that extra pass. They don't do any merging the first stage. Now, why do they have n divided by 7? It's because the stuff they start on is 1/7 the size of pages that they normally would start on. Because instead of going ahead and putting in, well, maybe I could put an n divided by 7 in here too, I suppose. Each of these sizes is not the number of passes has to do with how long it's going to take to bleh. It's a good example. Let's say I had 49 things to start. Okay? And I throw them in here. So what happens? How many times do I have to run it through? Am I making sense here?
In what?
Which technique?
I'm losing my bus of thought. I was trying to explain to you why the n divided by 7 is here, and now I got confused myself. It's not hard, I just got confused. So you think about it for a minute while I get unconfused.
I guess it's because you started with a chunk of 7 instead of a chunk of 1. Over there you start with a unit of 1. You start with a unit of 7. So therefore...
Right.
So therefore you're
Right.
guessing the step.
Right. When you're through pass 0, Jacob's right. When you're through pass 0, what happened here in their first pass? They took one page at a time, they threw them out. They still have the same number of pages they had to start with. Right? That's in the binary case, after pass 0. They bring them all in, they sort them all out, they have the same number of pages they start with, so to go through the number of passes is still log the number of pages. But here, after pass 0, what are the size of your runs? They're 7 pages long, right? Because I've done 7 at a time.
So we're reading in all 7 and sorting them all.
Sorting and merging.
You're doing like a quick sort on all 7 pages of those things.
Right. Actually, they don't sort and merge. They just sort them all, spit them out, kind of what I wanted to do in the binary case. And then you get things of size length 7. And then your n divided by 7 comes from there, because you only have n divided by 7 left. Basically, they finally come up to the way that I explained how it should be done when they do this improvement. And that's why they start with what they think is simpler before. Ugh, this isn't so important, and I'm confusing you more than helping. If you understood this, that was fine. If you understand that, great. And if you don't, don't worry. All right, I want to do a couple more things before we quit, though. All right. 2 more things as far as how improvements can run. You know there's a trade-off between the CPU time and the I/O access time. And now we're going to come back to something that Chris mentioned a minute ago. The idea that if you read a lot of pages in at once, starting from a certain spot, that's much more efficient than reading each of those pages in individually. Because if you read them all in at once, you don't have to do the seek and rotate for each one of them. You just do seek and rotate once and then transfer. Since the disk access time is a big, big issue, you'd like to knock that down. So what if we try to knock that down?
How is it different from this really, except that this is a ceiling?
Well, here presumably we brought in 1 page at a time here. That we didn't bring these consecutive 6 pages in.
In order for this to work, they have to be consecutive on the disk. So that requires...
Right.
forethought.
Right, but we didn't read them all in.
But if you were reading in n pages, why would you do it anything but consecutive?
You'll see in a second. What if we went ahead and read in things, say, three at a bunch? What happens then?
The cost involved is...
We speed up as far as the disk access go. So I want to know what you lose. That's what Jeff's asking. What do you lose? Why don't you always do that?
Well, for one thing, the data has to be there on the disk in this fashion.
Yeah, but we can do that. We're pulling things in. We're pulling things in, that need to be merged. They're already sorted, and very quickly the merged lists or the merged runs are longer than the number of pages we have. So we can do that pretty soon in the algorithm. So what happens when we bring in just 3 at a time? Why are things any worse if they are? Well, what happens when you do this is that we're kind of back to the binary case now again. You're taking a bigger clump of things and a bigger clump of things and merging them together, and the number of passes that it takes actually goes back up. Instead of log base 6, it becomes log base 2 again.
It then goes down by a factor of 3.
The size of the n changes, right. And the cost for each disk access changes. So this is another trade-off. If the size of the blocks that you're reading in get bigger, then the number of passes gets more, but the cost to access them gets less. And you need to do a calculation to see if it helps or not. So that's one more little twist to the various variations you can do. One last thing, and then I will quit. Oh, there's 2 last things. I take it back. One quick last thing, and then one thing that I need to spend a little more time on. But one quick thing. The book talks about this idea of double buffering, which I want to mention briefly because it comes up in other contexts. This is a separate idea, and it comes up in other things, like when you're writing a program that does graphics, and sometimes it's really slow, and some people say, oh, well, we got double buffering, and now it's working well. And what's that all about? Ever hear anybody blab about that when you're doing your ball program in the Java thing? No? All right. Well, I'll blab about it right now. Here's the idea of double buffering with respect to sorting. The idea is, when you go to the disk to access something, what happens? The CPU says, I need this value. It's not in RAM. Go to the disk. What does the CPU do then? Do you remember this from the hardware course?
Need something to be working on.
It waits. It waits. Right. It's got a little instruction that says, don't do anything until I get something in my memory data register and I can go to my next step. Bum-ba-dum-ba-dum. And it's a long wait relative to CPU cycles. A long, long wait. So you want to have the CPU do something else, just like Chris said. You want to have the CPU churning away at something else. And machines are built nowadays that they can do that. They can wait and do other stuff, and then they get a little interrupt that says, hey, okay, I'm ready. It's standard. The I/O says, wake up. And then you get the I/O, and then you can continue dealing with the I/O. But in this algorithm, that's trouble. Because when this buffer runs out, we cannot continue. There's nothing to do. We cannot keep merging because it could be that the next smallest one is the one that's going to appear here. We have to wait. We have to fill it up. So what do? So we have this idea of double buffering. We keep double copies of all of these. And when you read stuff in, you read 2 in at a time. Then you start doing your merging on this one. When one of these runs out, you say, I/O, go get me another one. And while it's getting you that one, you copy this one in here. So you can work on the second one that you already had sitting there while that second one gets replenished. I have no idea how realist streaming video works, but maybe there's some idea that relates to that. The idea is that you have to be able to do something at the time that you're processing the thing that's coming through.
So it's not really a copy of the...
No, it's not a copy. It's the next one. Right. So it's a double buffer. This is a buffer, and here's another buffer that feeds into the buffer.
In this case, they would actually have been like 3 each or something, right? Since we're still limited by how many pages we can store. With the same.
Yes, I would have had to chop this down to 3 and 2 copies of each if there were only 7 pages in the thing, right? I'm assuming here that there's 14 pages available. Yeah, no, Chris, you're right. You'd have to cut down. You only have a finite number of buffer pages. That's true.
How would that affect your operating time?
It would certainly change it if you have a fixed number, right? So, but again, it's a trade-off. So you get smaller numbers here, which makes the cost greater, but you get speed up in the CPU processing time. And when is this useful? It's useful as long as the time it takes to process one of these runs inside the CPU is at least as long, or about as long, as the time it takes to read in the next page of I/O. Because if this is going to finish processing the next one and it still has to wait, then what's the point of wasting all this space and cutting down this number? You want to balance it perfectly. So this is very much fine-tuning, and this is very much an art, and this is very much what a good engineer can do, and it is not what an algorithms person would work on. It's what somebody who is proficient and used to the system would work on. All right. One last topic, and then we're done. And this topic is related to everything, but I'm keeping it separate because the book kind of puts it right in the middle, and you think it's something very, very fundamental. And you should realize that it's actually something that is not used in any system. It was, I think, presented in a paper about 3 or 4 years ago. It's not used in any system because of technical constraints that most record sizes are not the same. And to make this trick work, you need to have record sizes all be the same size. But nevertheless, it's an interesting idea that I don't think I should skip. And I want you to see it. And I'll tell you what it's used for and what the idea is. Let's review what we've done in the past. In this case, if we have 6 buffers, we fill them up, we write them out. 6 things come in, 6 things come out, and the size of those things are 6 pages long. So if there's 6 buffers, the things that come out are 6 pages long. Okay. Now, this method is a way so that past 0, instead of generating things that are 6 pages long, even though there's only 6 buffers, 1, 2, 3, 4, 5, 6 buffers here. Instead of generating things that are 6 pages long and past 0, this is a method that on the average generates things that are 12 pages long. So it changes this n to n divided by 12 instead of n divided by 6. It's that kind of improvement. It's a very small improvement, but it's a cool idea. So you should see how it works. And the best way to see how it works is with an example, because you're tired anyway and you're not going to get it if I don't do an example. So let me do an example. Here's the idea. Actually, we had 7 buffers, right? We had the 6 in and the 1 out. So we're going to use, instead of reading 6 things in and oh, let's bring that kitty up here in the front. Come on, let's put the kitty on camera just one time. Come on. And does he have a name yet?
We seem to be going with Etsy.
Etsy. Okay, so here, Alex, this is Etsy. Meow. Okay. All right, here's the idea. We got these 7 buffers. Instead of just reading them in and reading them out and getting things of n divided by 7 size, we're going to use these buffers in a very different way to try to get runs that come out that are about twice that size on the average. And here's what it looks like. I'm going to do an example with pages of size 2, just to show you what it looks like. And here's how it starts. It's going to be, this example will make it clear, so don't worry. Okay, 1, 2, 3, 4, 5. Pages of size 2, 5 pages here, 1 page here, and 1 page here. Okay. Here's the 7 pages. Instead of reading in 7 things and spitting out the sort of those 7 things, instead we're going to fill up these things, fill up this thing, and now we're going to go into a different mode completely. We are not just going to sort them all together. We're going to try to get bigger collections, bigger than all the things put here. So keep in mind then, therefore, we're going to have to fill up these things more before we give up on this pass-through. So pass 0 is going to come up with bigger size blocks. Here's how it works. Here's the input buffer. Here's the output buffer. Think of this as just one big collection. There's no ordering here, just one big collection. What we're going to do now is we're going to look through this collection. We're in RAM now. We're going to look through this collection and find the smallest one. Okay? So it's 6. We let the computer do it. 4, thank you. That 4 is gone. What replaces the 4? Well, in fact, all we do is we just copy over the top to the top, the bottom, and the bottom. We don't do any calculation. So 16 replaces it. Just pass the next one in. Now, if 16 replaces it, well, let's do the next one here. What's the next smallest? 6. And 11 replaces 6. Okay, so do the first 2. Replace them. This now gets out. Goodbye. If it's out, I put a line through it. This is now gone. It's inside somewhere else in the RAM. So we need to fill this up again. And in comes more information. This is the key thing. We are not done with this run yet, but we're pulling in more information already from the disk. All right, what's the next smallest? 7 and 7 and 10, right? 7 and 10 go away. In comes 3 and 8. Okay? So this is now gone. This is now gone. And in comes 24 and 2 from the disk. And what's the next 2 to go in there? All right, so now let's think. The whole idea of this is I am supposed to be spitting out a sorted run. I'm supposed to be spitting out a chunk of things that's sorted so I can begin my merge external sort with pass 1 the normal way. I'm trying to get something that's going to be longer than this 5 or 6 pages long, something maybe 10 pages long if possible. So the problem now is, as you can see, because it's random the way the data comes in, I cannot necessarily get everything in perfect sorted order here. In fact, it's hard to predict just how sorted it's going to get. For example, the 3, which is the smallest one in this list, it is no longer possible to get that in the right spot without doing something complicated. So what do? Now I have to tell you what we really do to find the next number. It's not just find the smallest number. It's find the smallest number which is still bigger than the last one that we've done so far. So find the smallest one that's bigger than 10. 11 and then 12. So I cross this out, I cross this out, I cross this out. Into 11 goes 24. Into 12 goes 2. In comes new data, 7 and 9. I'm going to do a little more of this to make sure everybody gets it. I want you to see how far this can go. How far it goes depends exactly on what order the input comes in. It is not predictable. It is not easily analyzable. You have to do some complicated mathematics to figure out just what happens on the average here. And that's what they did in this paper. They analyzed it, they did some experiments, and they figured out that if you had 6 buffer pages to start, that these things end up to be about 12 long before you get stuck. And you will get stuck. So let's keep this going until you get stuck. All right. I'm going to move up here. Is that okay? One more down. 13, 15. 13 goes away. 15 goes away. I put in 7 and 9. And my next data is 17 and 23. Okay, what's next? 16, 21. Oh, yeah. Who said that? The one who's always right? 16 and 18. So this gets 17 and this gets 23. Bye-bye 16, 18. And the next data that comes in is 1 and 20. What's the smallest one that's still bigger than 18? 21 and 22. Out they go. 21 and 22 get replaced with 1 and 20. Next data, 26, 28. There's only one more page after this. 23, 24 comes out. Goodbye, goodbye, and in this place go 26 and 28. And finally, the last piece of data, 25 and 27. What comes out now? 26, 28, bye-bye. 26, 28. In its place comes 25, 27. And now every single thing that's sitting in RAM is smaller than this list. So now this list is done. Out it goes back to the disk. It's a fairly long run relative to the 6 that I'd have. This happens to be about 8. On the average, you get about double the buffer pages you started with if you do some analysis. So this is a trick that the book very carefully goes out of its way to say nobody does. And the reason is that the overhead is a pain in the neck. And places like Oracle care about their bottom line and their stock price, and they're not going to put some kooky little idea like this in there until it really works. And one of the reasons why this doesn't work is because the size of these records is not exactly the same. And if it's not the same, it's a little bit difficult to somehow implement this strategy. And I'm not sure of the details, or I haven't really thought about why it's hard or easy. But keep in mind that it's not used, it's just a neat idea, so I left it separate for the very end. The book kind of has it intergrained in the middle. Don't get confused.
What's it called?
I don't know what they call this. I know the section it's in.
It's called the algorithm nobody uses.
No. Does anybody have a book? I'll tell you where it is.
Yes.
You got a book.
Is that what you're calling the heap sort?
No, it's chapter 11. They call this minimizing the number of runs with a big asterisk. They call this sort replacement sort.
So for the next...
It's 11.2.1. Yeah, Doug.
For the next run, would we start with the data that is left over from the previous run? Would that be the starting point?
Exactly. Right.
So the next run, we're going to have a tendency to have a better result because we've pre-selected for smaller numbers.
Kind of like an amortized analysis. If you have a bad one here, you get a better one here. Yeah, it's true. Yeah. Anyway, this idea, as you can see, I mean, there's no new algorithm here. You can't publish this in an algorithms journal. You publish this in a Proceedings of Database journal because this is just, hey, here's a cool, tricky idea that might speed up your database. And then one day, some things that the researchers do actually, can get fiddled with by the engineers, and then Oracle goes up another 1.5 on a rumor.